If you haven't watched the previous video within the playlist pertaining to normal distribution, I'd recommend doing so now. In this video, we're going to discuss how to navigate around a normal distribution, assuming that our data is normally distributed. We're going to do this in order to determine the probability of various events. This will be useful if you're in a Stat 101 course and you need to have a bit of information to help augment your learning. Remember, not all data is normally distributed. Only assume such if informed of such. We're going to be performing our analysis in RCommander. We're going to let the computer do the heavy lifting for us. So if you're in class and you're using the z-tables, this may still help you out, but we're not going to be using z-tables for this particular video. So let's begin. So there are many differences between the histogram and the probability distribution. Mainly among such is for a histogram, data is being displayed from events which have already occurred. Whereas with a probability distribution, this is a graphical visualization of assessment of probability as it relates to future events. So you can't find the probability of a specific event within a normal distribution. Don't be tempted to try. This differs from histograms where you can follow along the bars on the x-axis and then move up with the y-axis to discern the frequency of a particular occurrence. It's not the same as it pertains to probability distribution. A probability distribution is just a visualization. It's not actually displaying occurrence. The probability distribution is continuous. Again, this differs from the histogram. That means that there are infinite many numbers next to any number you can choose. And for this reason, again, you can't just select a certain observational value from a phenomenon, which you have the probability displayed for, and make a one-to-one comparison. You're going to have to move in between values. And this will become hopefully more so clear as we go through these slides. A bit more about histogram versus probability distribution. Frequency distribution is related to probability distribution. While a frequency distribution gives the exact frequency or the number of times a data point occurs, the probability distribution gives a probability of occurrence of a given data point. All right, so histogram is frequency and probability distribution is a probability mapping. In probability theory and statistics, a probability distribution is the mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. It is a mathematical description of random phenomenon in terms of its sample space and probabilities of events. We went over this a bit in the last batch of slides. This is Chebyshev's theorem, or the empirical rule, and it's stating that we would expect that if our observations were sampled from a phenomenon which is normally distributed, that we would find about 68.27% of those observations within one standard deviation of the mean, 95.45% of those observations within two standard deviations of the mean, and 99.73% of the observations within three standard deviations of the mean. So with that in mind, let's run through a few examples, and hopefully this will make clear what's going on. And we're going to be moving around a probability curve. So we went over the probability distribution in prior videos, the normal distribution specifically. And in this particular lecture, we're going to assume that all of the data that we're working with is normally distributed. So if you're told that the data is normally distributed, operate under that assumption. Otherwise, you'll have to test the data to see if the assumptions are valid. This is all going to hopefully make more sense as we continue on and get into the field of inferential statistics. This is sort of the first step towards the field of inferential statistics, because what we are trying to do is we're trying to make inference. If our data is normally distributed and certain assumptions are met, then certain characteristics that we would find in the normal distribution should apply to our observational phenomenon if our data is also taken from a data source which is normally distributed. And this will make more sense as we continue on. But as it relates to this particular lecture, let's get started here with our examples. You're currently employed as a statistician in a factory that produces flashlights. The senior statistician informs you that the premium brand of flashlight that the factory produces has a battery life expectancy which is normally distributed. So there's our key right there. Okay, so we're working with normally distributed data. The mean for the battery life of this particular brand is 20 hours with a standard deviation of 5 hours. So everything we need to work through this word problem is in bold. We needed the mean value, which is 20, the standard deviation, which is 5, and we know that the data is normally distributed. So that's helpful as well. So here's our probability distribution as it relates to this particular problem. Since the data adheres to a perfect normal distribution, we have a perfectly symmetrical distribution curve. So this is a perfect textbook normal distribution. We put our mean right in the center because, again, our data is normally distributed. And if the data is normally distributed, the mean will always be found right in the center. Now we're looking for randomly selected flashlights from the production line that last less than 6 hours. So that means we have to find 16 on our probability distribution. 16 is somewhere over here. And we're interested in the shaded region. The shaded region represents the probability. The shaded region represents the probability of occurrence of a value less than 16. Now, don't get confused here, all right? We're not looking for exactly 16. We're not looking for 16 or less. This is less than 16, not less than or equal to 16, okay? So if it lasts 15 hours and 59 minutes, it'll be found in this shaded region. If it is 15 hours, 59 minutes, 59 seconds, shaded region. But if it's 16 hours, it's not going to be in the shaded region. It's anything less than 16 hours, but not equal to 16 hours, okay? Keep that in mind. So I've already pulled up RCommander on my computer, so let's go through this real quick. And we're going to do the slides as well. So here is my RCommander in my RStudio session. Here we are. Now remember, there's two ways to initiate an RCommander session. You can either, once RCommander package is downloaded and appropriately installed, you can either click next to RCMDR in the Packages tab, or you can type library open parens RCMDR and run this bit of code to initiate the RCommander session. So here is RCommander. I already have it initiated. Okay, so let's take a look here. What were our values again? Less than 16 hours. Okay. So what we have to do is go to distribution, continuous distribution, normal distribution, normal probabilities. Our variable value is going to be 16. That's our X value, because remember, we're looking for less than 16. Our mean value, which was given to us in the word problem, that's 20. And our standard deviation is 5. We're going to go to lower tal because we want 16 here. We want the values less than 16. Less than 16, okay? Lower tal, less than. We click OK. RCommander creates the appropriate code and runs it for us. And our output is found here in the console window. All right. So if you were having trouble seeing that, this is what it looks like up close. Okay, same values. Here is the code that RCommander created to our liking when we put in the specifications. And here is the output value that was in our console. So we need to move the decimal point over 2 places. And once we've completed that step, we can now state our findings. The probability that a randomly selected flashlight from the production line will last less than 16 hours is 21.186%. We carried decimal point over 2, and then we rounded this 5 to 6. So 21.186%. So what is the probability that a randomly selected flashlight from the production line will last between 18 and 24 hours? Now remember, it's not equal to 18, it's not equal to 24 hours. We want any value greater than 18 and any value less than 24. It can get as close to those values as possible, but it cannot touch. So it has to be between 18 and 24. So 18 is here on our probability distribution, again, normal probability distribution, and 24 is over here. So we're looking for the shaded region, and this shaded region, that is the probability. If you were to sum up this entire bell, you would get the probability of 100% because everything would be shaded. And the reason that it's bell-shaped, and I don't think that we're going to get into this in this particular batch of lectures because it's a bit complex, is any distribution type is an integral. So if you had to take calculus 2, you might understand what an integral is. If not, don't really worry so much about it. But all of our probabilities distributions, whether normal or otherwise, are going to look something like this. And that's because they're all derived from an integral value. In any event, if we're looking for between the values of 18 and 20, we're still using the same mean and we're still using the same standard deviation. Our mean being 20, our standard deviation being 5. This is how we would perform this calculation. This is from RCommander, distributions, continuous distributions, normal distribution, probability distributions. Our x value is 18, because remember, we're looking between 18 and 24. Mean value is still going to be 20. Standard deviation is still going to be 5. And we're going to select lower tail, click OK. Now we have to do 24 also. In this case, the other x value is 24. Mean value is 20. Standard deviation is 5. And it's lower tail. Here is the output that we would receive in our console within RStudio for each one of these calculations. This is the 24. X is 24. This is 18. Here's the output, corresponding output. Lower tail in each case. And mean and standard deviation is 20 and 5 respectively. And the reason that we use these values is these are the values that we were given from the word problem. Remember, mean of 20, standard deviation of 5, data is normally distributed. That's why we're using these values here. So we subtract the one value from the other, and we come to this value here. We then have to turn this into a percentage. So we move this decimal over 2 places to the right. And the final outcome of such is the probability that a randomly selected flashlight from the production line will last between 18 and 24 hours is 44.357%. Okay, so this is a little tricky, so I'm going to illustrate what's going on in Paint. All right. All right, so let's try to do this then, all right? So this is our normal distribution. Pretend that this is a perfectly symmetric bell, okay? I know mine is not perfectly symmetric, but we're doing the best we can. And we needed the values between 18 and 24. So 18 would be somewhere over here. 24 is somewhere over here. So we're interested again, imagine that this is just straight up. We're interested in this probability right here. We're interested in the probability. Let's kind of make sure it's connected. Right there. Okay. So first what we're doing is when we're doing the first left-tailed test for 18 is we're getting this value here. Pretend that this is going on infinitely. All right. So this is what we're doing the first few menu options in RCommander where we're saying that our variable value is 18, our mean is 20, our standard deviation is 5, and it's lower test. This is what we're looking to discern as far as probability is concerned. Then when we're doing the same step, but we're doing it for 24, so in this case, variable value is 24, mean is 20, standard deviation is 5. That is this value here. It's both encompasses 18 to the left and 24 all the way to the left, including the shaded region for 18. So these are the two values which were output from entering the code into RCommander and looking at the output within the console. And if you remove this from this, so when we're doing the subtraction of the probability of 18 from 24, all that remains is this value here. So essentially we have this value, we're subtracting this value from it, and the remainder of that calculation is just this value here. Is just, sorry about that, folks, is just this value in the center. So again, we got the probability of 24 to the left, 18 to the left, and then we subtracted the one from the other to get the value in between. So let me go back to the slides. That's all that's happening here. Okay. This is 24 all the way to the left, encompassing the probability from 18 to the left. And this is 18 to the left, and we're subtracting the one from the other to get the value in between the two. And that is what remains here. Bit different here. In this case, we want the probability that a randomly selected flashlight from the production line lasts longer than 24 hours. Not 24 hours or longer, longer than 24 hours, okay? Same steps, similar steps, distributions, continuous distribution, normal distribution, normal probabilities. Our variable value in this case is going to be 24 because we want greater than 24. Our mean value is going to be 20. Our standard deviation is going to be 5. Because as you recall, those were the values from our initial word problem. And we're looking for a greater value. So in that case, it is the upper tail. Upper tail, not lower tail. Because lower tail, we're moving to the left. Upper tail is to the right. So this will be the code which shows up in our RCommander window. And this is the output which will be in our Studio console. 0.2118554. We move that decimal point to the right. And our final answer then is the probability that a randomly selected flashlight from the production line will last longer than 24 hours is 21.186%. All right, now you likely will not encounter these within your Stat 100 class. However, if you do happen to come across examples similar to what I have here, this is how you will perform the analysis as a relates to these inquiries. And we need to find the level of flashlight duration that only 25% of the flashlight selected will exceed, and also, or find the level of duration that 25% of flashlight selected will not exceed. First thing you need to do is you probably should just sort of sketch it out so you have an idea as to what part of the shaded region you're actually looking for. For the first, we're looking for the level of flashlight duration that only 25% of the flashlights will exceed. And for the second, we're finding the level of duration that 25% of the flashlights selected will not exceed. This is different in that you have to go to continuous distribution, normal quantiles. You then have to put in the probability. For the one, it was 0.75. We're still assuming the same mean and standard deviation, lower tau. And the other is 0.25 as far as the x value is concerned. And same mean and standard deviation, lower tau also. And this is the corresponding output for each. 23.372 and 16.627. So it's important to sort of just understand and work out what is actually being asked before proceeding when it comes to these particular problems. And really, as it relates to all the problems which we covered, you really sort of just have to sit down, underline what's being asked, make sure that the distribution type which you're going to be utilizing is indeed the normal distribution. It'll typically be mentioned in the word problem, and then proceed appropriately. In this case, the output is the level of the flashlight duration that only 25% of the flashlights selected will exceed is 23.37 hours. And the level of flashlight duration that 25% of flashlights selected will not exceed is 16.63 hours. So I hope that you found this particular batch of slides helpful. I know that this was a longer lecture than some of the others that we've been going through, but it's important stuff, and we're starting to really move into the meat of this sort of subject material. So if you enjoyed what you saw here, if it was something that was able to help you out, I'd appreciate if you would consider liking and subscribing. It would mean a lot. I appreciate you stopping by, and best of luck in your research or in your course. Take care and have a wonderful rest of the day.